Good morning, students. In unconventional machining process, unit 2, second half, we are going to see the topic called thermal energy based process. Introduction. In this method, heat energy is concentrated on a small area of the workpiece to melt and vaporize the tiny bits of work material. The required shape is obtained by the continuous repetition of this process. Example: electron beam machining (EBM). Second one, laser beam machining (LBM). Third, plasma arc machining, which is called PAM. First, we will going to see the topic called electron beam machining, which is called EBM. Introduction. In the electron beam machining process, high velocity focused beam of electrons are used to remove the metal from the workpiece. These electrons are traveling at half the velocity of light, that is 1.6 into 10 power 8 meter per second. This process is best suited for micro-cutting material. Principle: when the high velocity of beam of electrons strike the workpiece, its kinetic energy is converted into heat. This concentrated heat raises the temperature of workpiece material and vaporizes a small amount of it, resulting in removal of material from the workpiece. In EBM, the following two methods are used in EBM process. Types of EBM: machining inside the vacuum chamber. Another one is machining outside the vacuum chamber. First one is machining inside the vacuum chamber. Now you will see the construction of the machining inside the vacuum chamber of the EBM. The schematic arrangement of electron beam machining (EBM). It consists of electron gun, diaphragm, focusing lens, deflector coils, work table, etc. In order to avoid collisions of accelerated electrons with air molecules, vacuum is required. So the entire EBM setup is enclosed in a vacuum chamber, which carries vacuum of the order 10 power minus 5 to 10 power minus 6 mm of mercury. This chamber carries a door through which the workpiece is placed over the table. The door is then closed, sealed and sealed. The electron gun is responsible for the emission of electrons, which consists of the following three main parts. First one is tungsten filaments, which is connected to the negative terminal of the DC power supply and act as cathode. Second, grid cup, which is negatively based with respect to the filaments. Third, anode, which is connected to positive terminal of DC power supply. The focusing lens is used to focus the electrons at a point and reduces the electron beam up to the cross-section area of 0.01 to 0.02 mm diameter. The electromagnetic deflector coil is used to deflect the electron beam to different spot on the workpiece. It can also be used to control the path of cut. Now we will see the working. When the high voltage DC source is given to the electron gun, tungsten filaments wire gets heated and the temperature rises up to 2500°C. Due to this high temperature, electrons are emitted from tungsten filament. These electrons are directed by grid cup to travel towards downwards and they are attracted by anode. The electrons passing through the anode are accelerated to achieve high velocity as of the velocity of light, that is 1.6 into 10 power 8 meter per second, by applying 50 to 200 kilovolts at the anode. The high velocity of these electrons are maintained till they strike the workpiece. It becomes possible because the electrons travel through the vacuum. This high velocity electron beam, after leaving the anode, passes through the tungsten diaphragm and then through the electromagnetic focusing lens. Focusing lenses are used to focus the electron beam on the desired spot of the workpiece. When the electron beam impacts on the workpiece surface, the kinetic energy of high velocity electrons is immediately converted into the heat energy. This high intensity heat melts and vaporizes the work material at the spot of beam impact. Since the power density is very high, about 6500 billion watts per mm square, it takes a few microseconds to melt and vaporize the material on impact. This process is carried out in repeated pulses of short duration. The pulse frequencies may range from 1 to 16,000 Hz and duration may range from 4 to 65,000 microseconds. By alternating focusing and turning of the electron beam, the cutting process can be continued as long as it is needed. A suitable viewing device is always incorporated with the machine. So it becomes easy for the operator to observe the progress of machining operation. Next, we are going to see the EBM, which is machining outside the vacuum chamber. It is similar to the inside chamber. Since the fully vacuumed system is more costly, the recent development have made it possible to machine outside the vacuum chamber. In this arrangement, the necessary vacuum is maintained within the electron gun and the gas are removed as soon as they enter into the system. Next is process parameters. The parameters which have significant influence on the beam intensity and metal removal rate are given below. Control of current, control of spot diameter, control of focal distance of magnetic lens. First one, control of current. The heated tungsten filament cathode emits electrons depending upon the thermionic emission capability of the filament. It is given by Richard Dashman equation. J equal to AT square E power minus EW by KT. J means current density of the emitted current. W work function of the material, the filament. T absolute temperature of the filament. E electronic charge. K Boltzmann's constant. A constant. The above mentioned equation is valid only when the tungsten filament cathode is in free space. But in the presence of the electric field around the filament alters this current density very much. The grid bias voltage is used to control the beam current. The more negative grid with respect to the cathode, the restriction of electron emission will be more. Control of the spot diameter. The diameter of the spot depends upon beam current, accelerating voltage, magnetic lens, distance between gun and workpiece, etc. The most important three factors which contribute to change in spot diameter are given. Effect of thermal velocity. We know that the different electrons converging at different points along the longitudinal axis of the beam. So the spot size will get spread out and the minimum spot diameter is given. Second one is spherical deviation of the focus length. The spherical deviation results in the marginal rays passing the axis at a differential position from the rays. So it leads an ideal point image to the conformed in a disk whose diameter. Third point is control at focal length, distance of magnetic lens. The focal distance at magnetic lens is given by F by S plus D equal to 25 V means nothing but voltage divided by NT. NT is ampere turns in the lens winding. Next one is applications. EBM is mainly used for micro-machining operation on thin materials. These operations include drilling, perforating, slotting, and scribing, etc. Drilling of holes in pressure differential devices used in nuclear reactor, aircraft engines, etc. It is used for removing small broken taps from holes. Micro drilling operation up to 0.002 mm for thin orifice, dies for wire drawing, pots of electrons, microscope, injector nozzles for diesel engine, etc. A micro-machining technique known as electron beam lithography is being used in the manufacture of field emission cathodes, integrated circuits, and computer memories. It is particularly useful for machining of materials of low thermal conductivity and high melting point. Next is characteristics of EBM. Accelerated voltage 50 to 200 kilovolts. Beam current 100 to 1000 milliamps. Electron velocity 1.6 into 10 power 8 meter per second. Medium vacuum workpiece material, all materials. Depth of cut up to 6.5 mm. Material removal rate up to 40 mm³ per second. Specific power consumption 0.5 to 50 kilowatts. Power density 6500 billion watt per mm square. Advantages of electron beam machining. Electron beam machining has the following advantages. It is an excellent process for micro finishing milligram per second. Very small holes can be machined in any type of materials to high free accuracy. Holes of different size and shapes can be machined. There is no mechanical contact between the tool and workpiece. It is a quicker process. Order material can also be machined at a faster rate than conventional machining. Electrical conductor material can be machined. The physical and metallurgical damage to the workpiece are very less. This process can be easily automated. Extremely close tolerance are obtained. Brittle and fragile materials can be machined. Next is disadvantages. Limitation. The metal removal rate is very slow. Cost of equipment is very high. It is not suitable for large workpieces. High skilled operators are required to operate this machine. High specific energy consumption. A little taper produced on holes. A vacuum requirements limits the size of workpiece. It is applicable only for thin materials. At the spot where the electron beam strikes the material, a small amount of recasting and metal splashing can occur on the surface. It has to be removed afterwards by abrasive cleaning. It is not suitable for producing perfectly cylindrical deep holes. Thank you.